You are currently the only person in this conference.
Let's start recording. Please remind me to record all the lectures, because usually I get distracted at a certain point and we start the lectures without recording, and this is not very good. So, okay, this first, all lectures are structured in a certain way that we both speak for about 45 minutes up to 1 hour, let's say. And in between, we have a short break of 15 minutes, so you can stand up, get a coffee, and get awake again. So today I'll start the lecture. I will give a short introduction to magnetism, or even not so short. Let's see. It depends on you if you want to speak with me a little bit or not. And then Vittorio will continue with the first real lecture, because my lecture is more an overview of all the lectures and all the topics we will speak about in this course. And it's really a lot. So each year we have the problem to think about, we have a lot of topics to fit, because magnetism, after all, is a very wide field. But to give you an overview, it's important not to skip a few things, a few important basic things. And so we always have the difficulty of the choice. But at the end, the course is very, very full of a lot of topics. If you already studied or working in magnetism, then it will be easy for you to follow. But many of the students do not have experience with magnetism. Maybe they had only very short introductory lectures, and then it's getting a bit difficult, let's say. And that's why we put all the material on the website, and you can give a look. And please do that. You can give a look to the lecture that you heard, but you can give also a look to the slides of the next lecture if you want, of course. Then it's easier for you to follow the next lecture. So you can see here in this first slide, I hope you can see it very well, and I guess you can also put it on full screen, a lot of stuff on this table. And so I ask to you now, write something in the chat. What do you see, and what does it have to do with magnetism? So this is not my very messy desk that you see here. We put this on purpose. Okay. I don't even know who you are with the number S26. Could you write your name? Okay, sorry. Okay, I see. Now you are connected only with the email. Okay, yeah, we can see hard drives. Use magnetic domains to store information. Exactly. This here, I hope you can see my pointer, is the hard drive. I don't know if you ever opened it. Most of the computers had hard drives in their as a memory. Now, for example, my small computer that I'm using here at home does not have any hard drive anymore. It's using a flash disk, solid state drive. Somebody else wants to write something, please. Otherwise, we will lose a lot of time. I will wait until you write something. Credit cards, perfect. So also they have to do something, had to do something with magnetism, because now, of course, they are based on the RFID technology. So usually they only have a chip, but we put them there now because former times they had this stripe, this magnetic stripe on the back, which was used to store also their information and the memory. And of course, related to these stripes now is what you can see here, these tapes. So in former times, of course, I don't know if you still remember, it depends on your age. We used floppy disks, for example. We used these cassettes for listening to music. The students most likely never saw this kind of devices. But if somebody from the project listens, is a little bit older, he might remember this object. So these are classical magnetic memories. And we will speak about them, of course. What else can you see? So you can see here, for example, this small headset or that I also use. Also, this has something to do with magnetism. I hope you know. Loudspeakers, you know that they're of course using magnets which are moving a small membrane, and in this way you can listen. Charger, motors, perfect. We have something. So here in the back you can see this motor, electric motor. This is an AC motor, which we use in a drilling machine, for example. And here you can see the charger, of course. Also, this is using magnetism. And then you can see here, of course, we have these stickers for the fridge, and we have closure systems. Here, this is for the it does not come to my mind the word now at the moment. And you can see also some games. I also have it here. So, for example, here, this is already a very interesting game for kids, magnetic game, which is made of very strong magnets, neodymium iron boron magnets. I hope you can see here. The strongest magnets that we have nowadays. And we will speak about this in the lecture on hard magnetic materials, of course. So I see that something you know already about magnetism. But what I wanted to show you with this slide, is that there are a lot of things, that are magnetic in our world. So usually we show this set of things to the kids when we do some dissemination at schools, for example. And we ask them, what is magnetic? And the first reaction is, nothing, maybe no. They do not recognize, besides maybe these toys that they use, which are magnetic. Of course, then they recognize that this is magnetic. But all the other things, they think it's not magnetic. So it's really amazing to see that instead, magnetism is everywhere. In our house, you can find it everywhere. And it's very important in technology. Why it's so important in technology? Of course, because we have a lot of interesting applications. One of the most interesting applications, and the people here of Hafenmark, of course, they know this, are motors, transformers, and generators. So this is one of the most important applications. But we have a variety of applications. You saw also power supplies, of course, which are very important, or magnetic recording. And here you can see the floppy disk that I mentioned that we used in computers instead of USB drives and so on in former times. So, of course, access control is related to that, and credit cards. Also, this you saw on the table. And then we have sensors. Sensors are nowadays very, very important. We'll use a lot of sensors. Now, for automatization, in our world, it's very important to have sensors, and magnetic sensors are very much applied, for example. But here, this, for example, is not a magnetic, it's a kind of magnetic sensor. It has something to do with magnetization, with magnetic materials, but it's a magnetostrictive sensor in this case. And they can be also used as actuators, of course, so moving things by magnetostriction. Magnetostriction means simply that the material changes its shape in a magnetic field. What else? Electronic article surveillance. Also, this has something to do with magnetism materials. Then magnetic resonance imaging. It's becoming more and more important for diagnosis and diagnostics and medicine. And then we have some special applications which we do not use so much, let's say, but also they are used, like magnetic levitation for the trains and so on. So I would say in our group, one of the most important studies that we did in the past and that we are still doing, as many of you know, is the research on materials for motors, transformers, and generators. And this may astonish you, no, because if you think that motors are known now for 200 years, yeah, it's almost exactly 200 years, the electric motor, of course. So it's strange that after 200 years, we still want to improve the magnetic materials we use in these motors. But this is due to the fact that motors are really, really used everywhere. So everywhere, because you know that in our household, you can find electric motors in almost all devices. Now, here's shown the microwave, the fridge, and so on. So there are a lot of motors everywhere, but also in the automotive application. So in a car, I show you here a slide where you can see all kinds of applications for electric motors. So, for example, performance-related motors, comfort-related motors, volume motors. No, you don't even think about that, but we have almost 100 different electric motors in our car. And that's really amazing. No, we have so many electric motors that we really don't think about, because if you think my cell phone here now, also this has an electric motor. Do you know where it is? It's very small, of course, this electric motor, but it causes the vibration usually. So very, very small motors are applied in many, many applications. And that's why we do research, because if we could improve the performance of a magnetic material used in motors, even very, very slightly, now due to the huge amount of material that we use for this application, we could still create a reduction of energy consumption, for example, which is really important, and why we do still research on these materials. And the second application that we also did, on which we did a bit of research in our group, is magnetic recording. And it's so important also because in 2007, there was given the Nobel Prize to Albert Fehr and Peter Grünberg, just for an invention, let's say, and that was related to this topic, to magnetic recording. So, you know, of course, or you may know that in magnetic recording, it was always considered to have some limits, some limitations, very important limitations. And it was not possible at let's say 30 years ago to think about, or more than 30 years ago, to think about hard drives that could store such an amount as they can today. So I have here my very small external hard drive. This is still a magnetic hard drive. Now they are really very tiny, small. And this hard drive stores now 2 terabytes. So it was considered, let's say 40 years ago, impossible to have a terabyte hard drive. You can see here that the storage density now with respect to time in this graph, and you can see that, sorry, so you can see here the increase of storage density in the last years. And this increase was exactly to the invention of Albert Fehr and Peter Grünberg. But not only that, so they really stimulated with their research a new field. They created a new field of research, and this is magnetic spintronics, let's say. And we will speak about this in the last lecture a lot. And but I guess you know what I'm speaking about. So Albert Fehr and Peter Grünberg, they became the Nobel Prize for the giant magnetoresistance effect. And this was really one important, very important step. So this increased the storage density on hard drives remarkably due to the sensor that we are using now on these hard drives. So the sensor with this giant magnetoresistance effect became much more sensitive, and in this way it was possible to decrease the size of a single bit enormously. And therefore the areal density increased with the first hard drives that were prepared by exploiting this effect. And while this effect was honored with the Nobel Prize in 2007, the effect was already applied in the sensors in 1997. So the research that was done on this effect already started in the 80s. So this was an important step, and this next step was perpendicular recording. Perpendicular recording, as you can see in these 2 slides here, means only that your single bit, which is stored on the hard drive, former times was magnetized in plane. So this requires larger size bits, because otherwise the bits would interact very much. While then one moved, let's say, in about the beginning of this century, we moved to the perpendicular magnetization, so out of the film plane. And this was applied in the first hard disk in about 2005 and 2006. And also this decreased again the size of a single bit and increased enormously the storage density on the hard drive. And that's why we have these very powerful hard drives nowadays. So let's move on to the history of magnetism. So I already mentioned a little bit about, let's say, the importance of magnetism in technology with all these applications. But I also would like to speak a bit about the history. And I would like to remember how research developed in magnetism, also because this is important for our lectures, let's say, because we will follow somehow this historical approach of magnetism also in the lectures. We will start from the first theories, let's say, and move to the later theories in magnetism. We will start from the first basic principles of magnetism, and we will move to some very developed topics in magnetism, let's say. And and by the way, it's also very funny and interesting to speak about history of magnetism. So you may know, of course, that the name magnetism comes from a material, and I usually ask this to the kids or to the students now, if you know what kind of material it is. And of course, it's already written here, but in this case, I will show you the material, and I will share my screen. Okay. So this is the material that gives the name now to magnetism. So this was found, this material, in a region former times it was Greece, now it's Turkey, Magnesia, and it's magnetite, so it's an iron oxide. Of course, you know this, and this is the only permanent magnet, let's say, natural permanent magnet that we find. And thanks to this material, to this natural permanent magnet here, humankind started to study magnetism, because it was very amazing to see that this material attracts iron pieces. You can see here, these very tiny pieces here. These are all iron pieces, and they are attracted in lines. And these lines, of course, are the field lines. So the lines of the magnetic field that are coming out of this stone. But nowadays we know that, but at the time when this material was found, of course, it was not that clear that there's a magnetic field around this stone. So magnetite, this is was called in former times also lodestones, and you find in most historical books, you find it called lodestone. Of course, we know all this from Greece, because the Greek people studied a lot magnetism, and we have witness of Greek studies more from Roman writers than later on, and therefore we know that already the Greek were very much interested in magnetism, and especially, let's say, starting from the animist ideas that described, let's say, magnetism as a kind of soul. So a magnetic material has a soul, and therefore it attracts iron pieces. Starting from that, they moved on to more, let's say, scientific ideas, like Epicureanism, and thinking about the origin of magnetism. Of course, for them it was very difficult to understand magnetism. Now we know why it's difficult now to understand it. But at that time, one tried, for example, to say, okay, in magnetite is very dry and it needs the humidity of iron. So this was some scientific explanation, one of the first scientific explanations. Of course, for us it sounds like complete nonsense, but at that time it made some sense. So we always speak about Greek people that studied first magnetism, but because we are in Europe. But here also some Chinese colleagues connected, and we think that in China, magnetism was known for much, much longer time. And they already studied magnetism, most likely about 2000 before Christ. So very important topic. I always find it very curious, because magnet in Chinese, I read, of course, I don't know, I don't speak Chinese, can be translated by loving stone. And this is also something very similar to the French language. So this is nice, because of course, you can imagine, no, since we have this attractive force, no, of course, it was somehow considered, and that's why also animists had this idea of the soul, no, there's an attraction, so there's love, of course. This is just some curious thing. We don't know actually when magnetism was really applied the first time. Besides that, it was attracting curiosity and studies. We don't know when it was used for the first applications. We know that in China, for example, you can find this first type of compasses here, and they are considered that they were used for Feng Shui, which is kind of theory of aesthetics. Maybe if somebody of you knows more about that, he can tell me. But it was not used, for example, for orientation, as we use compasses now. We don't know in Europe when compasses were first used for navigation, for example. But for sure, they were known in Europe in the 12th century. So this is clear. And we have, of course, then a lot of witness that they were used for navigation on the ships in order to orient your ship on the sea, especially if you go very far. But not only for navigation, I mean, of course, from this fact, from using the compass for navigation, one understood that there must be a magnetic field. No? And this magnetic field was studied. How are the field lines oriented, the poles of a magnetic field, and so on. And this all in the 12th century was written down by a European scientist, Petros Peregrinos, in the Epistole de Magnete. And he studied exactly this, what he called terella, so it was a sphere of magnetite, and he put some elongated iron pieces on them, and he saw what I showed you before with the magnetite stone, that they align in a certain way, and they accumulate, and then you have some lines. And nowadays, of course, we know that this is the magnetic field, and this described also the Earth magnetic field. And this is why we can orient ourselves with a compass. And at that time, all this was new. And this was also later then, let's say, studied deeper by Giambattista della Porta, and in his work, Magia Naturalis. But still at that time, you can see this was 16th century, there was a lot of superstition in this field. And you can see also by the title, so let's go back, by the title, Magia Naturalis, that of course, magnetism was always considered as something magic, let's say, because this force that you have is acting at a distance from the other things. And this is something quite strange, no? So two permanent magnets, we know that they repulse or they attract each other according to the poles that you have, no? So they can attract or they can repulse, no? But all this looks somehow magic. And describing, of course, these forces by a magnetic field and the field lines was already very advanced. And understanding that there are two different kind of poles, also this was quite advanced if you think about. Nowadays, when we speak to the kids about the compass, no, then they look at us and they almost don't know anymore what is a compass, no? Not what is used. So it's funny. They don't know that the Earth has a magnetic field. Although the magnetic earth field is very important for the development of life, as we know, the kids do not know that anymore. And that's really interesting because, of course, nowadays we have our applications in the cell phones, no? For you can orient yourself. Also here you have a small magnetic compass inside, but it's not needed anymore because we have GPS system. So who needs the magnetic field, no? But I think it's funny to understand that this was the origin of studies, no, of magnetism of humankind. So William Gilbert is considered the first one who really wrote a scientific book on magnetism. And it was called De Magneticisque, my pronunciation, of course, is terrible, Corporibus, et de Magno Magnete Tellure. So you can see also here, the Magno Magnete Tellure, of course, this is the Earth, no, which is considered a big magnet. So also here, the Earth magnetic field was very, very important for these studies. By the way, William Gilbert, he was not a physicist, he was a physician of Queen Elizabeth at the time. And I guess you can see here that he was a very prosperous man. So I guess he had no problems to finance his passion and to research in physics. So these are the things that were known already, but one of the problems was, of course, this superstition that was going on. And you will find in the additional material that I put on the website, a piece written by Giambattista della Porta, that he writes that at that time it was completely forbidden for the people that were working on ships, no, to eat garlic, because otherwise they were afraid that the compass will not work anymore if you breathe with your garlic breath on this compass. So this is kind of funny to read that, and I advise you to read this piece. Okay, let's move, but now finally to the first scientific theories. Unfortunately, you see, it's one century after that we have the first scientific theories on magnetism. Of course, everything started then with Descartes and rationalism, and one tried to understand better this natural phenomena. Coulomb, for example, he wrote his Coulomb laws, and he understood that the poles, magnetic poles, are inseparable. So while electric poles, of course, we have two different types, so two different kind of charges, magnetic poles are inseparable. Then Poisson wrote the first mathematical theory of magnetostatics, and this was in 1824. But let's say, more important, I would consider the experiment of Hans Christian Ørsted, because he found connection between electricity and magnetism. And this is really, really important because we still use this a lot, especially if you think about motors and generators. And he gave the experimental proof that a current creates a magnetic field. So an electrical current creates an electric field. And think about that. Just 1 year after the experiment of Hans Christian Ørsted, that was a very simple experiment. No, you let the current flow through a wire, and then you put a compass close to it, and the compass will move. So you see that there's a magnetic field. While without the current, there's no magnetic field. So 1 year after, Faraday already prepared a prototype of an electric motor. And this was a very simple electric motor, of course. Let's say one cannot even call it like that, but it was shown there that thanks to magnetism, electricity can create motion. And you can give a look to, there are some sites on the links of the Polytechnico site. In the links, you will find a Prezi presentation, and you can give a quick look there. And there's a link also to this motor. Maybe I can just share with you the screen quickly and show you this very simple Faraday motor. So you can, I will go. So you can see here that you have these magnets, permanent magnets, that he put in a liquid which conducts electrically, and that's why this wire, having an electric current for the battery, moves around here this permanent magnet. So this was the first electric motor of Faraday, and he did this experiment just 1 year after the discovery of Ørsted, so it's really remarkable. Another important thing that created this experiment of Ørsted was the first real theory that is still used, let's say, of ampere. So the idea was there that internal electrical currents are responsible for ferromagnetism. So in a ferromagnet, you have very, very small ring currents, and they each of them creates a magnetic moment, and in some you have a magnetic in your magnetic material. Of course, there were several problems with this kind of theory. As for example, pointed out Weber, these small electric currents would heat up the material, so one moved to microscopic currents. And of course, later on then, with the idea of the atom model, then everything became more reasonable, let's say, and magnetism was understood a little bit better. Faraday not only did this first experiment of an electric motor, he also did a lot of studies in magnetism. And in fact, he was considered by Maxwell the greatest genius, experimental genius at the time. And stimulated, the experiments of Faraday stimulated a lot Maxwell to write his theory on electromagnetism. So Faraday, for example, he understood that there are different kinds of magnetic materials. He did his experiments of the Faraday force, so that some materials are attracted by a gradient field and some are repulsed by a gradient field. But he also did, for example, he found the Faraday effect, so the rotation polarization of light passing through a magnetized material. So a lot of important studies, and important in a way that we are still using this effect. So there are measurements, of course, of magnetic materials based on the Faraday effect. And of course, the Faraday balance, let's say, we are still using. Maxwell, he was the first one to write the theory of electromagnetism that we use nowadays everywhere in describing applications of magnetism. So if you are an electrical engineer, then you know this, of course, by heart. Everything, the Maxwell equations are very, very important. And we will start in our course from that, more or less. And then we will move on, because that's not all. No, Maxwell is not all. Langevin in 1905 wrote his theory on para and diamagnetism. And why? In 1905 only, no? Because it was already needed to know something more, to know something about the structure of the atom, for example. It was known then the electron. And with the knowledge of the electron, one could imagine that these small ring currents are caused by one electron only, for example. And this creates a magnetic moment. So the angular momentum of the electron will create a magnetic moment, and this will be responsible for some kind of magnetism. And the Zeeman effect also was explained by this motion of the electrons, because you could, of course, split up spectral lines by inducing motions of electrons, let's say, in two different ways, now clockwise or counterclockwise. And what was not understood, unfortunately, is the anomalous Zeeman effect. So it's clear that we can split up spectral lines maybe in two lines, but why we have more than two lines? This was not understood, because there was still missing the full explanation of the atom model. After these years, of course, Weiss did his molecular field theory, and this was explaining then ferromagnetism, and also we will study this in the course in detail, but he also did another thing. He studied magnetic domains, and we will find that magnetic domains are very, very important to understand the behavior of magnetic materials. So what was missing, of course, here we still speak about classic theories, but missing was quantum physics. So quantum physics, Compton in 1921 proposed that the electron possesses an intrinsic magnetic moment, and this was the spin. So with the spin, of course, everything, we move from angular momentum to the spin momentum, and we move to another origin of magnetism. Gaudsmit and Uhlenbeck gave the theoretical proof of the electron spin, and Pauli implemented the spin matrix in the wave equation of Schrödinger. So this was then in 1927, and with this, finally, one could find an explanation of ferromagnetism, let's say an origin of ferromagnetism, because while Weiss only did a phenomenological theory of ferromagnetism, which could be very well applied, and in fact, we are still applying the Weiss molecular field theory, but some things could be not understood. And instead, Heisenberg and Dirac, they gave a real explanation of the origin of magnetism, and this was found in the so-called exchange interaction. The exchange is caused by an overlap of wave functions. So we need quantum physics. You have to consider we need quantum physics to understand the origin of magnetism. But in fact, let's say in our everyday life, we don't need quantum physics to describe most applications of magnetism. Okay, here I just mentioned in this slide then other topics which are related still to our course, which go beyond, because of course with Heisenberg exchange, research in magnetism is not finished. Not at all, let's say. There are many more topics that go far beyond this theory. So it's not, Heisenberg exchange cannot explain everything in magnetism. And many of these topics also we study in our group. And we will mention in this course, for example, band theory of magnetism, which goes far beyond the exchange theory, or density functional theory. You have to consider, of course, that you are in a many-body quantum physics state. In thin films, magnetism is slightly different than in bulk materials. Also, this you have to consider, because there are effects that do not occur in the bulk material, superficial effects. Then we have effects of magnetic resonance or excitation states like spin waves in magnetism, which is not described, of course, by static theories. And then one of the last research topics that were developed is spintronics, which is still coming from semiconductor theory, but from semiconductor research, but now it's very much applied in magnetism. Okay. already for 45 minutes. But I would like to go through these basic concepts of magnetism, maybe very quickly. So they are missing a few slides now, and then we will have 15 minutes break, let's say. So these basic concepts describe everything that you will listen in this course. But it's nice always to go back to the basic concepts when you then listen in the course something more detailed, because remember what is the most important thing. And one of the most important things is that all magnetism usually that we use in our everyday life is described in this concept here in the electric motor. So for example, we see already in this motor, I guess you know how it's functioning. Here we have a permanent magnet. Then we have some coils of copper, and these wires, by passing through an electric current, will magnetize this other kind of material, white one, this ring, and in this way you create a rotation. So this is one of the most important applications that we have, and we have already the concept that a current is creating a magnetic field. We have a magnetic field that is easily magnetized, a magnetic material that is easily magnetized, and we have a magnetic material that is not so easily magnetized, that stays always magnetized. So we have permanent magnets and we have soft magnetic materials. Everything already here, and everything described not by quantum physics, we don't need, by electromagnetism, so by Maxwell equations. Now, usually when we are in the classroom, I ask the people to describe what are saying these Maxwell equations, but maybe since it's late, I will not bother you too much, but maybe Vittoria will do that. So please get prepared what they mean, these Maxwell equations. However, what I want to say is Maxwell equations are sufficient to describe this application, but there's missing something very, very important. So I would like to ask you, but I'm afraid that you will take too much for the answer. What is missing, of course, are the constitutive equations. So in order to be able to describe our motor with the Maxwell equations, the theory is all contained in Maxwell equations, but we need the constitutive relations that describe how my material behaves in a magnetic field. Because if I don't know how magnetization of this material here changes when I apply magnetic field in the wire, then I cannot describe by Maxwell equations this motor. So constitutive relations will tell you how magnetization changes when you apply magnetic field, how polarization will change when you apply an electric field, and how the current will change when you apply an electric field. So this, of course, relates to conductivity, while this first equation here relates to susceptibility and permeability. I guess you already know that susceptibility gives you the relation between the magnetic field H and the magnetization M, and permeability gives you the relation between B and H field. Of course, here it looks like a proportionality, but remember, it's not proportional. In general, it's not proportional because chi, the susceptibility, depends on the magnetic field. Okay, so we need the constitutive relations to describe by Maxwell equations our motors. But how do I get them? I don't know them, no? And one of the ideas was the idea of Faraday, no? We could measure this susceptibility, for example. How can we measure this? And if we measure this with the Faraday balance, for example, no, we will find that we have very different kind of magnetic materials. Of course, when I ask the kids, what is magnetic on the table, no? The table that I showed you before, no? And they tell me, oh, nothing, or they show me one thing, two things, no? The important thing is that in reality, everything is magnetic because we have different types of magnetism, no? And this was already understood by Faraday. So, give a quick look, what is the difference between these different types of magnetism? So what is diamagnetism? Diamagnetism, if we measure and find the relation between M and H, we will find that chi is a constant. And the relation is negative. You can see here that we have a line with a negative slope. And in temperature, this chi is almost constant. In paramagnetism, we have a very different behavior. Let's say at higher temperatures, the behavior is very similar. Again, we have a proportionality. M is proportional to H and increases linearly. So chi is almost a constant. But at lower temperatures, it's not a constant anymore, because here we have the concept of pre-existing magnetic moments. So while in diamagnetism, we consider it is an induced phenomenon, so it will always increase when we increase H. In paramagnetism, we have already some small magnetic moments in the material, and of course a limited amount of magnetic moments, and we will only align them with the magnetic field. And this will give you this situation that at lower temperatures, you will also reach saturation of magnetization. So all magnetic moments aligned. In ferromagnetism, we have again our pre-existing magnetic moments, but we have another phenomenon, and this is exchange interaction. So you will have a spontaneous alignment, because each magnetic moment wants to align with all his neighbors that are surrounding them. And only due to this spontaneous magnetization, we have the phenomenon of ferromagnetism. And again, you can see that ferromagnetic materials behave similar to paramagnetic materials. But especially what is interesting to see is that at a certain temperature, they have a transition to a paramagnetic behavior. And of course, we will start this in the next lecture in detail, from where is coming this transition. And then we can also have antiferromagnetic materials, which is nothing else than ferromagnetism. But now our pre-existing magnetic moments will align antiparallel. They will not align parallel anymore, but they will align antiparallel. In this way, we have an overall magnetization, which is almost zero. And these materials were considered initially non-magnetic materials. But of course, they are magnetic. And there is even a very strong exchange interaction sometimes in these materials. So why, however, do we call only ferromagnetic materials really magnetic materials? So a kid would never say that a diamagnetic material, maybe he does not even know which material is diamagnetic, no, is magnetic. And the reason you find here in this chi, look at the chi. Here we have 10 to the minus 6 to 10 to the minus 5. Look at chi of paramagnetic materials, 10 to the minus 5 to 10 to the minus 3. And now look to ferromagnetism. Chi is up to 10 to the 5, plus 5. And that's why Faraday force is strong for ferromagnetic materials. And that's why I can attract with my small mag an iron piece very easily. Because although iron is very, very heavy, let's say, the force that we act by our magnet is strong enough to move the weight of a ferromagnetic material. And this is not the case for a diamagnetic material or for a paramagnetic material. So we can measure chi, and then we can put it into the Maxwell equations, and we can describe our motor. But can we also understand, I mean, can we use a top-down approach, a bottom-up approach to arrive to the description of my material? And in order to do that, you need to understand magnetic energies, and you need a thing that describes more coming from the origin of magnetism. Of course, this must not be the microscopic origin. It can be a continuum theory. And this is the case for micromagnetics and the micromagnetic theory, and this will be explained in detail by and the thing is, of course, that once you know all magnetic energies, you can do an energy balance. You can minimize this energy and you will find the magnetization state at the end. But you have to know all kinds of magnetic energies. And here I give you just some examples. One of the first ones that we heard already is exchange energy. But then there's also magnetostatic energy, as you will hear from Vittorio today. There's energy caused by magnetocrystalline anisotropy, for example. So this means that magnetization may have preferred directions in a crystal. Or there's magnetoelastic energy. So the energy state will be changed when the material is brought in a magnetic field and the material changes its shape. And then, of course, at the end, there's Zeeman energy, the classical energy of a magnetic moment when it is brought into a magnetic field. And the last concept that really we have to still to know to describe magnetic phenomena is the concept of the domain structure. Because a ferromagnetic material, of course, if we consider exchange interaction, would be always aligned. All magnetic moments want to align with the neighbors, and so they will all point in the same direction, and we will always have a magnetized material. But this is not the case, because we know for our iron ball here in my TRaMM toy, this does not behave like my permanent magnet in the TRaMM. The permanent magnet is always aligned. So exchange interaction is always acting here. Here also exchange interaction is always acting, no? But it does not attract another iron. Not attract two iron balls. But I can attract two permanent magnets, no? They will not stick together. And why do they not stick together? Because there's a domain structure. So overall, magnetization may be almost zero or very small, let's say. Although inside we have exchange interaction acting, and we have different regions where all magnetic moments are aligned. And this behavior is caused by magnetostatics also. And an energy balance will describe perfectly the creation of domains and domain walls, which are, of course, the borders between the domains. And with this concept, finally, we can describe our hysteresis curve. Because if we only measure a material, then we will find this kind of hysteresis, the relation between magnetization and magnetic field. But we cannot fully understand if we don't understand also domain structure. And two of the important quantities that you should remember in a hysteresis curve are coercivity and remanence, for example. Coercivity would be the field where magnetization becomes zero, and remanence is the magnetization when the field is zero, so the remaining magnetization, let's say. And domain structure will help us in the third lecture to understand this hysteresis curve, why we have this steep area here of the hysteresis curve, which is caused by domain wall motion, and why we have this flat area hysteresis curve where we have rotation of magnetization. Okay, then we will speak, of course, about the different kind of materials, soft magnetic materials and hard magnetic materials that now we understood already we have in our TRaMM toy. So the balls are soft, and then we have these hard magnetic materials. And let's move on very quickly, I would say, just to finish our lectures, and then we move to the special lectures. One will be given by Vittorio, and he will speak about magnetoelastic elastic materials and magnetocaloric materials. And this was one of the big research topics also in our group, that we studied materials that might be used for a magnetic fridge, for magnetic refrigeration, let's say, using magnetic materials state instead of gases for having the refrigerating effect. And then in the last lecture, we speak about magnetism and current. So we will speak about all kinds of effects related to magnetoresistance and, of course, giant magnetoresistance, which I already mentioned at the beginning. And then we will speak about spintronics. Okay, and I guess now already it's 1 hour, and we can stop here. Of course, if you have questions, I will stop recording, and please ask your questions, and then we will have a break.
So just give some feedback in the chat if you're here. And okay, it's 52. I think we can start. So this is the second part of lecture 1, and we will deal mainly with Maxwell equations here with magnetic media. So let's say that one of the aim of the course is introduce, let's say, a model, a theory, let's say, to describe ferromagnetic materials. And to do that, we have to put this theory of ferromagnets, that is called micromagnetic theory, in the correct framework. And the correct framework is those of Maxwell equations. So we will start from there. And in the sense, this lecture will be a sort of review of things that are known mainly in Physics 2 course of the university. The point is the following, that we have students from physics, from engineering. So sometimes what you studied at the university is somehow different. And so we start with a review of Maxwell equation in differential forms. So don't be scared too much, because we start with writing all 4 Maxwell equations in differential forms. So we will spend time, at least half of the lecture, to understand the details. So why do we write the equation of the electromagnetism in such form? And this was mainly due to Maxwell and many other researchers. This is the form that is commonly known and is also written in the international system, with the units of the international system. Okay, so let's start. We have 4 equations, no? 4 equations that are called, well, the first had to do with the electric field and the electric charge. This is the Gauss law. Then we have another equation that concerned with the magnetic field, the magnetic induction field. And we have no charges at the right-hand side of the equal signs. This equation tells us that there is no equivalent for the magnetic field of the electric charges. Absence of magnetic charges, we can say, we can call it. The third one is the Faraday law, one of the first of being discovered, by the way. And the last one is, let's say, the sum of the discovery of Ampere and the term added by Maxwell himself in order to make the equation consistent. So why these equations are important, and well, what they do describe, first of all? Well, they describe fields. They describe fields, and actually 2 fields, 2 vector fields. So at the left-hand side, we have essentially the quantities that we want to describe, that are the electric field E and the magnetic induction field B. These are the objects of our description. So we imagine that in space, in the whole space, there exist these fields. These are vectors and describe certain quality, no? Certain properties of electromagnetism that is described in terms of a field, of a continuous vector fields. And to describe electromagnetism, we need 2 fields, 2 vectors. At the right-hand side, we have what are called the sources. So Maxwell equations are a way to describe what are the means by which the electric and magnetic fields are generated. And these sources contain, many terms, but there are 2 terms that are different from the others. in terms that are real sources. So we have to introduce electric charge density, in this case, as one important quality, which is generating the field, in this case, the electric field. But also the motion of the charges is important. And this we do by introducing the electric current density, J, which is another source of these fields. And then we have other terms, no, that are derivative of the field and themselves in time. And these also will be sources of this field. There are, apart from the fields, then now we have looked at the equation, and we found that we have the field themselves, the sources that are charges and the electric current density, but also we have constants there. And the constants are the mu0 and epsilon 0 constants. And these are called the permeability of vacuum and the permittivity of vacuum. These two are related each other, no? And the product of the two is 1 over the speed of light squared. Well, here we have to say, to anticipate something, that this will be dealt in the next lecture, observing also the evolution of how different measuring systems have dealt with this constant, for example, the GGS and the international system, and how the change in the international system have dealt with this constant. So up to now, these two constants are related, by the speed of light, which is fixed, and for the rest, they can be measured. So as you see there, mu0 used to be 4 pi 10 to the minus 7 area over meter, but now is something that can be measured and has to be measured. And this is the value which is written there is, we will touch this point in more detail in the next one. So both mu0 and epsilon 0 are constant physical constant. So accept them to have them fixed for the moment. Then we will discuss how we could possibly measure them. Okay, so as we have sources, electric charges, and electric current densities, and the fields, what remains to be understood is what is the shape of the fields that will be generated as a consequence of the charges and the electric current density. And this is given by the particular form of the Maxwell equations. That is what we have on the left-hand side, which is operating on the fields. And these operators are written in terms of the nabla operator. So the operator nabla is the generalization of the derivative. So if we operate with the derivative on a vector field, well, we can operate in very different way. For example, if we operate by taking the divergence, this means that we take that field, which has 3 components, we make derivative over each component on the corresponding dimension in space and sum up. This operation, which is quite complicated, means to take the divergence of the vector field. And this divergence is a scalar. So if we look at the equations, the first two, we have the divergence of the field E and the divergence of the field B. And both of them are equal to scalars. The result is not a vector, but is a scalar. This is valid for any point in space. And for the electric field, this is equal to the charge density divided by the permittivity of vacuum. And for the magnetic induction field, is equal to 0. More complicated is the curl. So we can operate in a different way on the vectors. So we can, let's say, take the external product of the divergence of the nabla operator with the field, and then we obtain the curl. The operation of the curl is written there in the slide at the end. So the result of operating the curl is to produce another vector field. And this vector field, this is what the last two Maxwell equations tells us, are equal to what you find on the right-hand side. Okay, so this is very interesting, but in differential form, I mean, we are not able to learn much on the structure of the field. So we will try to understand more by using two very important theorems of differential analysis that we will try to explain in very simple form. The Gauss theorem and the Stokes theorem. Let's start from a certain vector. No? So what you see there as a sketch, you have to imagine points in space where at each point you can assign a value of a certain vector field. Could be either the B field or the E field. Now we will make an operation on this vector field. So for example, instead of taking the full space, we delimit a certain region of space and we define a certain surface. If we do that, then we can take the surface, we can take the normal. For example, in this case, I selected a surface which is closed. Then in any point of the surface, easily, I mean, not easily, but I assume that I can define the normal vector. So the vector pointing outside the surface itself. And then I can compute a quantity, which is again a scalar. And this quantity is a flux, is the flux. The flux is a quantity that you can define in so many different phases. It means that you take the vector, you project the vector along the normal at the surface, and you just sum up over the whole surface that you have. This is clearly completely analogous to the flux of a quantity, like be the gas or a fluid which is flowing, a velocity or whatever. But it can be done with any vector field. So this flux, again, is a quantity. It depends a lot on the vector field and also on the surface that you have selected. But what can we do with this flux? Well, what helps is the existence of very important mathematical theorem of vector analysis, which is called the Gauss theorem. And the Gauss theorem tells exactly what is written there. If we compute the flux of this vector field over that surface, which is closed, the surface sigma, then this flux is completely the same thing that you would get if, instead of integrating over the surface, you would integrate over the enclosed volume, but not integrating, I mean, the vector itself, but the divergence of the vector field. This is very interesting because it means that not all qualities of the vector field determine the flux, but only the divergence, the part of the field that gives a non-zero divergence, determine the flux. Now let's take this mathematical result and apply to our case, to the Maxwell equation. Well, the first, we have exactly that. The divergence of the electric field is equal to the charge density divided by epsilon zero. Well, now our red arrows, take them as the electric field. Again, take a surface, project the electric fields along the normal. You can compute a quantity which is the flux of the electric field. What is the result of the Gauss theorem? That instead of computing this flux like that, you can simply take the volume and integrate the divergence. But the divergence, we know from Maxwell equation, is given by the charge density. And as we have a density, then the integral of the volume over the volume is just the total charge. We have found something really interesting. So the flux of the electric field, which is exiting a certain surface, is equal to the total charge, which is inside the volume, divided by epsilon zero. This has a lot of consequences on the structure of the E field. So if you imagine you have a distribution of charges somewhere in the space, what happens? It happens that the field will have points or region of space where it's starting and other points where it's ending. What we compute here is not the whole electric field. As we will see, we have other Maxwell equations. But if we are in static conditions, so nothing is changing in time, then this is the true electric field. It depends only on the charges. This is the static component of the electric field. Fields like these are called gradient fields or conservative fields. They have these special properties of being, well, the divergence is equal to something. The interesting thing is that these gradient field or conservative fields, they admit a potential. So in electric phenomena, we can always introduce a potential in space. And the electric fields can be defined as the gradient of this potential. The electric field has sources and sinks. So if you take two charges, like in the cartoon there, you will have electric field exiting, pointing outside from the charges of one side and pointing inward from charges of the other sides. This is a particular shape of vector fields that is let's say, specific of the electric field itself. But we have seen that in Maxwell equation, we have also an equation on the magnetic field, where we have the divergence. And this is divergence of P equal to 0, absence of magnetic charges. Now this is clear, because as we have learned before, it's the electric field that has charges. If the magnetic field is equal, the divergence is equal to 0, it means that the structure of the magnetic induction field is completely different. And in particular, it doesn't have the quality that we have seen before. But do not have it means a lot of things. For example, the magnetic flux computed over closed surface is equal to 0. But then if I imagine to split the surface in two, it means that the magnetic flux is something which is conserved, The conservation of magnetic flux comes directly from the absence of magnetic charges. Then we have a lot of no, and the no is that the magnetic induction field does not admit the potential. So we cannot write, like we have done before, the magnetic field as the gradient of some potential. It does not admit the potential. So we cannot do the same way like before. There are no charge-like sources. The magnetic field is conserved. The quality of this field is completely different. And this is called a divergence-free field. That is a field which has 0 divergence, or also solenoidal field. All these words you understand that are taken from physics. Now, even these, in the end, are quality of the mathematical description of vector fields. Solenoidal field, because it's the field which we will see later, is generated by currents, electric currents. Okay, so to understand more, we have also to introduce another theorem. So Gauss theorem is not enough. We have also to understand a little bit more of what happens if we take the curl on a vector field. Now take again another vector field like the one in the sketch there. No? Is not exactly the same, and you will understand immediately the reason why also the drawing, the sketch is a little bit different. Because now the aim is not to select a certain volume in space, but select a certain path. So I can always take a path in space, and I can make another mathematical operation, what is called a line integral. This is a little bit more tricky, no? The idea of integrating the flux over a surface is more familiar, and this it seems a little bit more, a little bit less. But if you think of electric current, this is exactly what to do. You consider the electric current which is flowing through a wire, and then you integrate over the wire itself. So imagine to do the same thing for a vector field. Select a path, no? And the path will be closed. Then, in every point of this path, you take the vector which is along the path, then you project the vector along that unit vector, and you just sum up. The result, again, is a scalar. So can we say something about this scalar, which is not, I mean, it doesn't involve the whole quality of the vector field F itself, but just a part of them. To say something, we can use the Stokes theorem. And the Stokes theorem tells the following. It's a little bit more complicated than before, but try to follow. Now, we have a line, no? So the Stokes theorem tells that the same results of this line integral you obtain if, instead of the line, you consider the surface, which is no more closed now. It's a surface which is enclosed by the path. So that surface, on that surface, you can take the curl of the vector F and then compute the flux. The flux exactly as we have done before. So if you do this operation, you obtain exactly the same result that you obtained before. So the line integral. At this point, it means that only the curl of the F contributes to the line integral of that kind. No? So the curl of F is another vector field. Then you project along the normal, you sum up, you compute the flux, and this is the scalar, which is exactly equal to the line integral. Now let's apply this to the remaining two Maxwell equations in order to understand more about the structure of these fields that are generated. On the Faraday laws, what we can do? Well, we use now again the E field. We know that the curl of the electric field is equal to minus the derivative in time of the B field. Let's plug the two fields in the Stokes equation as before, and we will find the following. We have a certain path where we compute the path integral of the electric field itself. But at the right-hand side, we will have the curl of E, the flux of the curl of E integrated over the surface. But the curl of E is equal to the derivative of the magnetic induction field in time. So consider to fix the surface, and then you can take the time derivative out and compute just the flux of the B field. But this is something we already know, is the magnetic flux, is the flux of the magnetic field. So this is Faraday law as very often explained. So the circuitation of the E field is just minus sign, the time derivative of the magnetic flux. Very nice way to pass from differential forms and integrated forms. Okay, but what we can learn about the structure of the E field, of the corresponding E field? If we have a magnetic induction flux which is changing in time, then we also have an electric field which is generated in space. But this electric field is completely different from the one generated by charges. This, if we like, we can call it a dynamic component of the electric field, because if it is static, there's nothing. This component, it does not admit a potential. So very often, if you want to state the Faraday laws in terms of the integral form, you don't speak of an electric potential, but rather of an electromagnetic force. So the integral of the E field. This field, only this part of field is solenoidal, has the property of being exactly like this. The path integral, the integral of the field is equal to something. Let's proceed, and let's make also the last one, which also is very well known. Because now we have last equation where we have the curl of B, which is equal to the sum of two terms. For the moment, let's leave the time derivative of the E apart. And let's just take the electric currents. So now again, we take the B field, we compute the integral over the path, we make the circuitation of the B field. And what do we discover? We discover that this result is nothing else than the flux of the electric current density over a certain surface. But integrating a current density over a surface means to just compute the current. So the circuitation of the B field over a certain path is nothing else than mu zero times the electric current which is traversing that surface. And this is nothing else than the Ampere laws. Very nice, because now we have learned that the magnetic induction field has sources, and these sources are the electric currents that are generally present in space. So the electric current density is the source of the magnetic induction field, but is the source in a completely different equation for a field which is solenoidal. If we have a variation of the electric field in space, we have what are called displacement currents. These are called like this because if you take epsilon zero times d over dt, this is the same unit of the electric current density. So you can interpret this as a sort of displacement current. Very good. And by the way, this was not discovered by, let's say, where the discovery of this Maxwell equation comes. The one here was discovered by Ampere, one by Gauss, one by Faraday. They take the name. The absence of magnetic charges has no, let's say, I think this was also by the work stated by Maxwell himself. In, let's say, the idea was that if you break into a permanent magnet, you cannot isolate poles, positive or negative magnetic poles. So absence of magnetic charges come from there. But the very true point is that was Maxwell himself to discover the last term, and this was introduced by symmetry. So something which is very important in Maxwell equations. So the discovery done just by discussing the structure of the equation as they are. Okay, with this we have done a short overview of Maxwell equation, both differential form and integral forms. But now there is a very big question mark, because up to now we have discussed electromagnetism, but we are in a course of magnetism. So, and magnetism for us means magnetic materials, matter which is magnetized. And there is no place of magnetized matter in Maxwell equations. I mean, or at least, where is this place? Because we have seen charges, we have seen electric currents, E fields, B fields, but if we have a piece of magnetized material, how can we put this effect of matter inside the equations? This is a big question, no? So it's something which is not obvious at all. So we need to understand more on how, of what there is inside magnetized matter that makes this matter special. And here we have to make, let's use this cartoon, no, to describe these things, because this was done already at the beginning of the development of electromagnetism, because scientists in the 16th century, they were already playing a little bit with currents, with permanent magnets, and they do all these things by knowing very, very, very little, no? And there is one very interesting observation which was made by Ørsted, no? So where he essentially made the following observation by playing essentially with a very simple detector of magnetic field that were compass needles and a very basic generator of currents and piece of magnetized matter. But there is one question. What does it mean that B is solenoidal? B is solenoidal when the divergence of B is equal to 0. So in a sense, these definitions are exactly related to the definition itself that I gave before. So any field where the divergence is equal to 0, and then we'll have other sources, will be called solenoidal. And every field where the curl is equal to 0 will be called, let's say, a potential field. So it's solenoid, B is solenoidal in this sense, and the electric field generated by the charges and nothing else is a potential field. Hope I answered. Okay, I proceed from Ørsted. So the observation, okay, thanks. The observation is the following. So if I make this experiment, trying to detect the magnetic induction field, Ørsted deduced the following. If I use a wire with an electric current, for example, a current loop, or if I use a piece of permanent magnet, I do not see any difference in the action that I can see in space on a compass needle, no? In the language of Ørsted. If we use modern language, we would say, if I have a wire with an electric current, which is exactly what we have seen in the Maxwell equations, I produce a B field in space. But again, in modern terms, if I put a permanent magnet somewhere, then also I produce a magnetic induction field. And they have no means to say that these fields are different things, that they are exactly the same thing. This is the observation by Ørsted. And then immediately in time, I don't know, but it immediately can come to your mind, then to make an hypothesis. And so, and that is to suppose that magnetic material, the piece of magnetized matter, contains inside, in some microscopic region, some current loops. So this is called EMPIR hypothesis. That was exactly done by EMPIR in order to explain why you have a magnetic action due only to magnetized matter without any external generated electric current. So the idea is that you don't know, at the time at least, but it's very clever if you think about it. You have no mean to see what is inside matter. You have no microscopy, you have no quantum theory, you have nothing. But you can imagine there is something very small that you cannot detect, but the quality of that you have inside is the same of a current loop or some microscopic current flowing. And this is a very smart idea, even if, now we can say no, but magnetism is not due to true electric current because we have the electron spin, which is contributed to magnetism and so on and so on. But in the end, the way we introduce magnetism in Maxwell equation is related to this EMPIR hypothesis. And how it's done? Well, it is the following. So imagine that you have at a very microscopic level, we could say in modern language, atomic level, some current, some microscopic current, electronic current or orbitals or whatever you can imagine in a more modern language, if you like. But if something like this, then what to do with microscopic current? You have to use them in Maxwell equation as we have seen before or not? Well, yes and no, but we could say yes. For example, well, let's make a passage in between, because this is one of those good points that we always meet when we want to describe physical phenomena by continuous equations. So let's speak of in modern terms. Now we have atoms. We have atom with angular momentum, spin angular momentum, something which is related to the atom themselves. But in Maxwell equation, we don't want to see any atoms, because we want to look at matter as something which is continuous. So how can we pass from the continuous to the discontinuous? Well, the point is the following. We have always to make the hypothesis that continuous description of matter is in terms of moving averages. So we don't, even if there are sources that are at the atomic scale, we don't want to see that atomic scale. So we average them out. This has a lot to do with thermodynamics. So we know that macroscopic behavior of matter is related to the fact that the result is always the average of something that occurs at a microscopic level. Suppose that you take a small volume and you make the average, then you don't see atoms anymore. You will have, for example, qualities like charges, like currents and whatever, but averaged over that small volume. If you want to make this passage compatible with thermodynamics, you have to imagine that this small volume is not too small. So it's small enough to permit you to have still a continuous description of matter, but large enough to contain what is called a thermodynamic amount of atoms. So let's say in modern terms again, the volume should be large enough to allow the statistics to apply. So you have many things that they do different things, but on average, they do the same. Moving averages. This is important to say because from now on, all the quantities that we will define and treat, like the fields and charges and magnetization, where we introduce them, and whatever will be the result of a moving average. So we always smooth atoms out. I mean, in modern terms, by talking about atoms. Very good. So if we do like this, even if we don't know much about these microscopic currents, if they are atoms or molecules or whatever, we can make this moving average and introduce what is called a magnetizing current. So the result of the average of this microscopic current over a small volume. This magnetizing current are again only the effect of magnetized matter. So something that is not under our control. We cannot generate them. They are there for some reason that we don't understand for the moment. So we accept that in certain materials, or in principle for any material, we can have magnetizing current inside. But now we could also, we could also like we can elaborate more about that. Instead of the truly microscopic that we don't know much, we introduce this description in terms of magnetizing currents. Take a magnetic body, no? If we take some region of space where this effect exists and other no, so for example, a piece of magnetic material, then you also have to introduce another thing. So the fact that this current, they do not exit the body. And so the divergence of the magnetization current are equal to 0. And this is the crucial passage, the next one. Again, if we have the divergence of a vector which is equal to 0, we know that we can always write this vector in terms of a curl. So introducing the magnetization current or introducing the magnetization is the same. Instead of using the magnetization current that are not clear enough to us, we can introduce another quantity. So a quantity that we call M, and if we take the curl, the operator curl on the M, we obtain exactly our magnetizing current. Why is this important? It's important because we can give a physical meaning to this M vector. And this physical meaning can be understood if we make one passage that I do not demonstrate here, but I just write. There is an important quantity in electromagnetism, which is called the magnetic dipole moment. We will see later. We will see in the next lectures much more about the magnetic dipole moment. But for the moment, let's stick at this. This is a quantity that I compute for a distribution of current. So if I have distribution of current that I generate, for example, loops, solenoids, or whatever, I can compute the equivalent magnetic dipole moment, but by making an integral. And essentially is the written integral, which is written here below. So if I compute this integral for this magnetizing current, I can use the fact that this magnetizing current is equal to a curl. But if this magnetizing current is equal to a curl, the whole procedure to compute the magnetic dipole moment of this distribution of current is extremely simplified. And the simplification turns out to be exactly that the magnetic dipole moment of a distribution of a magnetizing current is nothing else than the integral of the vector M in space, in the volume of the system. And then we arrive at a direct and quite important interpretation of the vector M. M is nothing else than the density of magnetic moments. So independently of what do we have at the microscopic level, currents, spins, or whatever, M that we call magnetization is density of magnetic moment that we may have at microscopic level. This is very nice because it simplifies a lot something that we don't know much in detail, and we cannot know much in detail. So we have taken all the burden and complexity of the internal structure of the matter that gives rise to magnetism in terms of another vector field that is called demagnetization, and has this important property of being nothing else than the density of magnetic moment. So we have to admit that there exists magnetic moment at some microscopic level. And then we can just use the density of magnetic moment as an additional field that we have to add to Maxwell equations. So we have to add something, to add the magnetization field to Maxwell equation. And how to do that? Well, there will be a very strong price to pay. Because if you do like this, then we would like to say that in the Maxwell equation where the electric current appearing, we have to split. We would like to take the current that we generate with our solenoids, with our, our way to generate the current that are under our control in one place. And to put all the current that comes from this microscopic current, this magnetizing current, in another place. Then we would like to split, to say that we would like to have Maxwell equations where we have only current that we can apply and to leave the matter in another place. And the correct vector to use will be M, so the magnetization, the density of magnetic moment. But the structure of the equation is nice in this sense, because the current density appears exactly where we have the curl of B. So if we imagine that instead of J, you put J plus by Jm, and instead of Jm, you put the curl of M, then you could write the Maxwell equation, the fourth Maxwell equation in a different way. In particular, you can take the curl of M on the left-hand side and have the curl of another field, not B, but B minus mu0 times M. What to say? You can, for example, think of this in this way. You could say, well, I would like still, if I'm in a magnetized matter, to use Maxwell equation in more or less the same form. But if you would like to do like that, you have to introduce another field. This field is called the magnetic field. Then, if I do like this, I can take again the fourth Maxwell equation in a similar way. I can say that now it's the curl of the magnetic field, which is equal to the current density, the one that I apply, plus the action of the displacement current. This is very nice because it looks like the previous one. But the big price to pay is that now I have no more just a magnetic induction field, but I have three fields describing the magnetic phenomena in magnetized matter. I have the magnetic induction, the magnetization, and the magnetic field. So the fact that I introduce the magnetic field is a direct consequence of the fact that I've introduced magnetized matter. Big price to pay, and we will see a lot of consequences of this field. This field is important. It's important because this is the field that then we generate as experimentalists in our laboratories and so on and so on. But the true magnetic field is a magnetic induction field. This is the one that obeys to all the nice properties as being solenoidal and so on and so on. We can already anticipate something. The magnetic field itself is not solenoidal. We will see this in the next lecture in very much detail. In a sense, the magnetized matter acts as sort of a source. So we have to take a lot of care when we think about the difference with the magnetic induction field and the magnetic field when there is magnetized matter. It's clear that if M is 0, all this is useless. Very nice. Oh, well, not so much nice, but for sure we can rewrite all Maxwell equations in matter in terms of now the new field. The point is the following, is that the same thing that we have discussed in the details for the magnetized matter is also true for matter that can be polarized at the atomic level. So, for example, what is electric charge density? We have not discussed this into the details. For example, if I have a molecule which is polar, no, and then I have one part of the molecule which is plus and one part which is minus, but I cannot separate these charges. Is this a true electric charge density that I want to put into the Maxwell equations or not? No, it doesn't work like that, because I have to introduce this fact that depends on the matter itself in another way. So I have to call this a polarization of the matter. So again, introduce the fact that I can have charges because the matter has a certain quality. No, it has a quality that can separate charges. If I do like this, also the electric field is not enough, and I have to do something else. And this something else is called the electric displacement field. The electric displacement is the sum of the product of epsilon 0 times E plus the polarization of the matter. If I do like this, I make something similar of what I've done before with the magnetic field. But then I end up with the equation of Maxwell equation in matter, where I have a big price to pay again, because now the electric charge density are the true charges that can freely move. So if, for example, the charges that can go into a capacitor that I can charge and whatever. The electric current density is a true electric current that I can generate. For example, it's the current that can flow through a solenoid and whatever. But then the price to pay is that at the left-hand side, I have no more only the magnetic induction field and the electric field, but two of the equation are changed. They are no more for this field, but I have to introduce the electric displacement. So the Gauss law in magnetized matter is the divergence of the electric displacement equal to the free charges, densities. The second remains the same. The Faraday law also remains the same. And the fourth is also completely changed. So it's the curl of the magnetic field that will be equal to the electric current density plus the displacement current of Maxwell. These are the equation of a Maxwell equation in matter that we have to deal with. It's clear that something is missing, so it's not enough. So use this equation, while before, for example, if I could say that in vacuum, if I have the distribution of charges and the distribution of currents, I can compute all the electromagnetic fields everywhere. This is no more the case. Why? Because we don't know what the magnetized and polarized matter is doing. And we have the E fields and the D fields that depends on P and M. Therefore, something is missing. So this something missing are called, Michaela was mentioning this before, are the constitutive equations. For example, if I have nothing that can magnetize, M is equal to 0. This is a constitutive equation. Instead, if I have a paramagnetic material, the effect of a magnetic field could be to generate a magnetization in the same direction. If I have a diamagnetic material, then the magnetization will be opposite with respect to the field. And even worse, if I have a ferromagnetic material, this will be magnetized even in the absence of the field. This is the whole complexity of the constitutive equations. We will spend a lot of time understanding ferromagnets, where the constitutive equation between M and H not only is not linear, but especially is hysteretic. And this is the whole interest and importance also in putting magnetic material in Maxwell equations. How this is important? Very much, because all the calculations that you would like to make in a transformer, in a motor, in any magnetic structure has to pass from here. So you not only you have to describe all the details, electrical details, for example, of your machines or your device, but you need the constitutive equations. And we will see that for ferromagnets, soft ferromagnets, hard ferromagnets, not so soft or not so hard, these constitutive equations are really complicated. So for the moment, you can just remember these. They are nonlinear, so it's never possible to say magnetization proportional to H, and hysteretic. So you may have different value of the magnetization for the same value of the field. And this depends on what you've done before, previous history. And this is extremely important to take into account for any design of an electromagnetic machine. And the same is true for P itself, for the polarization of materials. In that case, also, you may have material that polarize linearly. You may have ferroelectrics that have hysteresis. Then there exists also multiferroics, so materials that both magnetize and polarize. This is just to mention, but we will not touch these too complicated issues for this course. Okay, so I'm quite close to the end. So if you want to read more, well, what I've discussed here essentially comes from books of classical electrodynamics. Jackson is a very good reference that I like very much. Then magnetized matter. We often reference the book of Giorgio Bertotti, which is dealing with physics, and the initial part on Maxwell equation and in magnetostatics is very well done, very simple and complete. Then, for those that would like to learn or know a little bit more about what happened to Maxwell equations after the revision of the international system, there is a very nice paper, quite recent, by Ron Goffard, but we will touch this in the next lecture in more detail. Okay, so for the moment, I could stop here. So it's more or less 1 hour. And if there are questions, I think we have time.